In this presentation, I am going to explain slip power recovery scheme in using static Scherbius drive. This is used for speed control of slip ring induction motor below and above the synchronous speed. Previous presentation I already explained regarding the static Kramer's drive. Coming to the concept of slip power recovery scheme, if Pg is the air gap power, that is the power injected from the stator into the rotor circuit, out of that 1 minus S times Pg is converted as mechanical power, that is Pm equal to 1 minus S times Pg. The remaining portion, that is S times Pg, is called slip power. In rotor resistance speed control, this slip power is dissipated in the rotor resistance, and in that case the efficiency is also very less. But instead of wasting the slip power in the rotor resistance, it can be controlled by converter, and that can be fed back into the line so that the efficiency can be improved. That is done in the slip power recovery scheme, that instead of dissipating in the rotor resistance, that power is injected into the grid. Now there are two methods of implementing this. One we call it as static Kramer drive system, and another one is called static Scherbius drive system. Static Kramer drive system I already explained in another presentation, that can be used to control the speed of slip ring induction motor below its synchronous speed. And static Scherbius drive system, that can be used to control the speed of slip ring induction motor below and above synchronous speed, or subsynchronous and supersynchronous speeds. Static Scherbius drive system, that can be used for controlling the speed of slip ring induction motor above and below the synchronous speeds, that is for subsynchronous and supersynchronous speed control. That consists, there are two converters, or sometimes we call bridges also. There are two bridges, bridge 1 and bridge 2, or converter 1 and converter 2, and to the stator 3-phase supply is applied, and from the rotor power, that is slip power, is rectified using a 3-phase control rectifier. That is, a converter 1 is a 3-phase control rectifier, and this DC another is given to another converter 2, and the output of this converter 2 is connected to the grid through a transformer, and the ratio of the stator to rotor turns ratio is equal to N, and the ratio of the transformer from the source side to the converter side is equal to M. Therefore, in this case, comparing with a Kramer's drive system, the input side diodes are replaced by thyristors. You can control the firing angle of these thyristors, and you can vary the DC voltage here. Similarly, you can control the firing angle of these thyristors so that the power flow can be controlled. Therefore, the two converter 1 and converter 2, in the case of a static Scherbius drive system. If the diode rectifier in the rotor side in static Kramer drive is replaced by a thyristor bridge, the slip power can be controlled to flow in either direction. The slip power can be flow from the rotor into the grid, or from the grid into the rotor. Both can be implemented if you are replacing the diode by control rectifiers or control converters like converter 1 and converter 2. With the bidirectional slip power flow, the drive can be controlled for motoring and regenerating in both subsynchronous and supersynchronous range of speed. That is possible in the case of static Scherbius drive system. Now let us see how static Scherbius drive system can be used to control the speed of slip ring induction motor above synchronous speed, that is supersynchronous speed. In that case, as I told you, the two converters, converter 1 and converter 2, converter 2 is working as a rectifier. Therefore, the AC line voltage is given to here, and that is converted into DC voltage by converter 2, and that DC voltage is converted into AC, or that is working as an inverter. Converter 1 is working as an inverter and converter 2 is working as a rectifier, so that the power from the AC grid is injected into the rotor, and by controlling the power flow into the rotor, you can control the speed of the slip ring induction motor above synchronous speed, super synchronous speed. Therefore, here in super synchronous speed operation, additional power is fed into the rotor circuit at slip frequency. And in that case, bridge 1 operates as inverter, that is bridge 1 is operating as an inverter and bridge 2 is operating as a rectifier. Or you can say that one, in order to work it, this is an inverter and this is as a rectifier. As you know that one, alpha 2 should be, this is alpha 1, that is alpha 1 should be more than 90 degree and less than 180 degree. Similarly, alpha 2 should be in between 0 and 90 degree. So this is working as a rectifier and this is working as a inverter, so that the power is flowing from the grid into the rotor that at the slip frequency. Therefore, the slip power flow from the grid to the transformer bridge, to the transformer, and then bridge 2 that is working as a rectifier, and then bridge 1 that is working as a line commutator inverter, and then to the rotor. This is the path of power flow from this, through the transformer, through this rectifier, and through this inverter that is injected into the rotor. Therefore, by controlling the power flow from the grid into the rotor, you can control the speed of slip ring induction motor above synchronous speed. That is the application of static Scherbius drive system in super synchronous range. Now let us see how static Scherbius drive system can be used to control the speed of slip ring induction motor below its synchronous speed, or subsynchronous speed control. In that case, the role of converters will be reversed. Then the converter 1 will be working as a rectifier. Therefore, the slip power is rectified and converted into DC, and that is converted into AC by the second converter that is working as an inverter, and that power is flown into the grid through the transformer. Therefore, in that case, subsynchronous range, the rotor slip power, that slip power is injected into the grid through the converter 1 which is working as a rectifier and converter 2 which is working as an inverter. Therefore, in subsynchronous speed control of induction motor, slip power from the rotor circuit is pumped back into the AC supply. And in this mode, bridge 1 is operated as a rectifier. Therefore, this is operating as a rectifier. Therefore, firing angle will be in between 0 and 90 degree. And bridge 2 is operated as an inverter. The firing angle between more than 90 degree, between 90 degree and 180 degree. Therefore, in subsynchronous speeds, slip power flows from a rotor circuit, then bridge 1 or the converter 1 that is working in a rectifier mode, to bridge 2 that is working as an inverter mode, and that is passed through the transformer and to return to the AC supply. The power flow will be in this direction. Power flows in this direction, that is coming into the, injecting into the grid. By controlling this power flow, you can, the power flow can be controlled by controlling the firing angles. By controlling alpha 1 and alpha 2, you can control the power flow from the rotor circuit into the grid. Thereby, you can vary the speed of slip ring induction motor below the synchronous speed, or subsynchronous speed control of synchronous motor is possible using static Scherbius drive system.